14.1, we're going to talk about the general characteristics of light. Now, light in itself, the concept of light, the study of light in physics, is a huge, huge portion of physics. We're going to talk about light. We're going to go into 14.1, and we're going to look at 14.2 and 14.4 together. I'm personally not, so like when you study engineering, you study specific things. I didn't study electricity and magnetism, but I know enough about electricity and magnetism to teach you about it. But this isn't one of those topics that is my forte, I would say. So there's a lot more about light, if this interests you. There's a lot about lenses. There's a lot about imagery, using like virtual images. That's where a lot of things like virtual reality come into play now. And it's a huge field that's evolving more and more. The concept of holograms, touch screens, all these things involve light, the study of light. So there's a lot more to it than what we're going to go into. All right? So feel free to investigate if you're interested in this stuff. Some students in the past take it upon themselves just to, read more about the material, read more about topics, or watch some videos on topics they find interesting. So feel free to do that. We're going to talk about the components of light, the EM spectrum, what it's made of. We're going to talk about the fact that it has a finite speed and why that's important. How brightness is affected by the distance from the light source, which you know already. Take a flashlight, and you shine a flashlight from here to the table, it's real bright on the table. Take a flashlight and shine it against the wall 20 feet away, it's much dimmer. It's obvious, you know that, but we'll discuss why. And then we'll talk about wavelength and EM waves. Okay, wavelength and EM waves. So to start, let's take a look at the actual form of an EM wave. So remember the term transverse from last class in 12.3? We talked about transverse and longitudinal waves. And we knew transverse waves oscillated up and down while traveling left to right. So look only, please, at the yellow part. Is anyone colorblind here? I've asked that earlier. Anyone colorblind? You can be honest, it's okay, you're colorblind. My brother is.
Hardly.
Oh, can you see the different colors here?
Yes.
What colors do you see mixed up in your color? Because this is about light.
It's like red green. It's something my grandpa had.
Okay, so you don't see the red and the green as well, right? You see like shades, is that what you see? Yeah, that's what I've known as most common. Anyway, this is blue and yellow, but just asking. So follow the yellow only, please. Follow the yellow only. The yellow, and I'll follow along the curve here, is an oscillating electric field. That's this right here. Okay, I'm following this wave right here. But what we'll notice here is that coming out of the page, this is like coming out of the page, literally, is a magnetic field in blue here. And they are transverse waves, and they're also perpendicular to one another. One of the waves is traveling towards you like this, while the other is traveling towards you like this. Okay, so one is oscillating up and down and moving that way. One is oscillating left and right, but also moving towards you. And they're moving along the same path, along the same direction where the EM wave travels. So an EM wave is titled an EM wave because it has two components to it. Okay, it's got a magnetic field and an electric field, so we call it an electromagnetic wave. This concept of EM waves is really important because there's going to be a huge range of EM waves we're going to look into. And they have different characteristics because of their frequencies, because of their wavelengths. So we're talking about like microwaves versus gamma waves, actual visible light versus ultraviolet or infrared light. What is the actual difference there? And what applications do they have? So this is going to be really geared toward applications, this idea of this concept of light. So let's take it for a moment.
We kind of did this in bio a little bit, I think.
Oh, good. How far into it do you go in bio? Do you talk about like the actual eye itself and how the eye works?
Yeah, like all the different kinds of lights and like where'd you go and stuff. That's like for second grade.
Oh no, you should know the idea of the spectrum of visible light. But that's a very small, and you're going to see, look at the spectrum of visible light. It's a tiny span, only 300 nanometers in the difference between the maximum and minimum wavelengths. Yeah. The other spectra are much greater. The visible light spectrum is a very, very, very small part of the EM spectrum. But yeah, you probably did learn about some of
that.
that.
What I remember is we didn't have like the range of numbers, but we had like a whole thing of like light, and then there was like a little like small like.
Yeah, a little bandwidth.
Yeah, that was like this is what you.
Yep. There's an interesting like webcomic I saw a while back. I probably have it if I pull it up on my computer. And it's like on one axis is the pitch of frequencies humans can hear for sound. On the other axis is the frequency of wavelengths humans can see for light. And humans are a very small part of the sound frequency bandwidth. Like we don't hear a lot of sounds that are higher pitched. And then we're a very small portion that we can see. So it's like this is how much of the universe you're actually experiencing. And the actual graph is like this big, and it's like this tiny pixel that we are actually seeing and hearing. But there's so much more on those spans. We can try and pull it up afterward. But Benno, it's along the idea of what you were saying where it's a very small portion of it. All right, so we're going to talk about different waves, and some of them are obvious based on their names, obviously, as you know. But specifically, we're going to take a look at the different ranges of frequencies and wavelengths and how they're applied. So we'll start with, in this case, radio waves. And what we're going to see here is that radio waves have the highest wavelength. Let's jot that down real quick. This is the highest wavelength up here. And you can see it if you take a look at the data down the middle. Okay, radio waves have the highest wavelength. And then at the very bottom, you have gamma rays with a very small wavelength. And that has a range of wavelengths on the scale of nanometers and beyond, actually, much smaller than nanometers.
Isn't that the whole thing?
Yes, Hulk was affected by gamma rays, that's right. Yeah, that's how he, transformed. Because of, obviously, take a look. The size of the wave, and I was going to get to this at the end, but I might as well bring it up now. The size of the wave is so small that it can penetrate your molecules. It can affect you on a molecular level. So these kinds of rays are used for treatment for cancer. So cancer cells and stuff, to kill cancer cells, to actually try to isolate those, they use this sort of radiation. Now, this radiation is good, but it obviously also affects people that have healthy cells in addition to those cancerous cells. It can hurt them as well. So that's why people get very sick when they're taking treatment for some sort of cancer. And it's understandable, but we're looking for better solutions. And the newer ideas for cancer treatment are really breakthrough, the ideas that they're getting through. They're trying to come up with these little nanobots that can specifically target cells in the body that may be refusing, the normal processes involved in the human body. So hopefully one day we won't have to worry about gamma radiation or using cancer radiation to help cure people, and it can be something that's more specifically oriented to those cells using little nanobots that can be programmed using computers. All right, so back to radio waves. They have the highest wavelength. If they have the highest wavelength, what else could you suppose they must have? The lowest frequency. And in this example from your text, they use a lowercase f. I've been using that omega symbol, that W. So if you want to replace that, you can, as long as you know that it's the same thing here. Okay, but this is the frequency that we're talking about, and you can tell because of the units. So if you want to relabel this as omega, you can. Doesn't matter. They're all the same thing. Frequency, they're called. Just look at the units, it's in hertz. So the highest wavelength has clearly the lowest frequency, as Alejandro mentioned. Okay, the lowest frequency. Radio waves specifically, they're not really used for televisions anymore. When were they used for televisions? When were radio waves really used for televisions? Anyone know?
Like the 50s?
Yeah, specifically. What did the television utilize at that point in time? Yeah, exactly. They had antennas. And if you're using radio waves to broadcast your television, you're still using an antenna. It still exists, you can still do it, but there's regulations now on what's called digital TV versus analog TV, using an antenna. But that's what radio waves are really used, to transmit radar, to transmit AM and FM radio, and then old TVs. Microwaves, obviously, from microwave ovens, because they're called microwaves for that reason. And microwaves, specifically, we can see become shorter in length, but larger in frequency. And what we're going to notice is as we move down the table, we'll see that the wavelengths get smaller and the frequency gets larger, obviously, because they're inversely related to one another. But microwaves used in radar, atomic and molecular research, and then some navigation. What do you find interesting, though, about navigation in recent times? Anybody follow technology feeds online? Anybody follow things that talk about new I don't know, not warfare, but like military stuff. There's some cool breakthroughs that they're having now. So microwaves are used to keep track of, where the enemy aircraft is. If it's in your radar zone or in your proximity of a certain, I don't know, hub or major city. Well, as recent as I think like 7 or 8 months ago, the U.S. had a stealth fighter that now was like undetectable by radar. And it used these methods that bend waves. Like, so the actual microwave or whatever they're using to detect where the aircraft is able to actually bend it around and allow it to go continue through. When really what used to be was like, it sends a wave, it hit an object, it pinged back. The time it took to get back indicated how far it was away. If it took longer for the wave to get back to the source, the plane was further away from the source. As the plane got closer, the wave would get returned much quicker, right? Well, what if the plane, instead of returning a wave and bouncing off, it had some technological feature to its surface that enabled that signal to wrap around the plane and continue onward. So it bends those waves and it becomes undetectable by radar. Okay? So that's the spectrum, or the part of the spectrum we look at. Infrared. Infrared specifically, how many of you like photography? Anyone do anything with photography? You're going to be using a lot with infrared radiation here, or infrared waves. Also, if you've ever looked at your remote control sends out an infrared signal. Anyone have an app on their phone to control their TV at home?
Yeah.
You have it?
Yeah.
Which one do you have?
The Roku app.
The Roku app?
I have the Apple TV.
You have the Apple TV one on your phone? Anyone else?
Yeah, I mean, I used to have, if you're trying to get at something, I used to have one that like had like an IR thing on it that you could like control with it, but it was really funky.
Well, that's exactly what it is. It's using your phone and it's sending out an infrared signal to the TV to change the channel or change the volume.
Like the Apple TV app.
Well, that might be different. I've used it for so I have a Samsung TV at home, and the Samsung app, that's a TV remote. It's the same remote for no matter what Samsung TV you have. So they made an app that literally mirrors the remote. You swipe up and down, you see the remote, and you literally use the buttons. And then you could open the guide, and if you have, I have Time Warner Cable, I swipe to the right, and it pulls all the Time Warner Cable data. And if I tap a TV channel, so what was I watching last night? Anybody ever seen Forgetting Sarah Marshall?
Yeah,
Yeah.
very good.
It's fun.
It's like-
Right? It's good. With the guy Marshall from How You Met Your Mother. Jason Segel.
And Russell Brand.
Yes, that's right. It's not a phenomenal movie, but it's fun. So anyway, it was on repeat, so I was just doing other work. I was writing a quiz I wanted to give you today, but I'm going to postpone it. I'll tell you at the end of class. Because some people didn't check their email already. He came up to me this morning asking about it. So on the remote, when you click the actual channel, it sends 3 pulses to the TV. We've talked about pulse waves now, right? 3 pulses. Those 3 pulses are the 3 channel numbers. So let's say it's on like channel 110. It sends 110. Well, how does it do that? In my senior engineering class, they're doing a project right now where they have to reverse engineer a product. And one of the groups is actually using a Time Warner Cable remote. They've taken it apart, studied the functionality of it, how does it physically work, what does it do. And what they've noticed is that every time you press a button, a different resistor, and we'll talk about circuitry this year, a different resistor makes contact with the button. And it sends an IR signal to the TV with a different wavelength, or it must be a different wavelength, I'm thinking, I'm not 100% sure on that. It's got to be a different frequency or wavelength that's sending for that IR signal that tells the TV, turn to channel 3, turn to channel 4, type in 3, or type in 4. And your phone, what it does is it replicates the remote. And it works on phones that are, phones, I guess newer phones, or phones that have this infrared signal that it can send. So usually a lot of brands like to match up. So if you have a Samsung phone like a Galaxy or something, there's a good chance it works with old Samsung TVs. And I'm guessing you have an iPhone? Yeah, because you said you use it on AirPlay, right? Or Apple TV. So infrared waves. Let's see what else I want to think about for this. How in physical therapy would it be applied? How would infrared be applied in physical therapy? How many of you gone to physical therapy before? Think about how it could be applied. An idea?
I was going to say to see things. kind
Such
of like an
as?
X-ray situation, but for like muscles or
Okay. All right. Maybe to see things. You could see temperature of muscles as they're being worked.
yeah.
Okay, so you can see how the muscles functioning. That might help. What else? Heart rate? I don't know for heart rate. I think for heart rate they'd be using something else to detect the pulse. Have you ever gone and they use like these little things that create vibrations on your back? You feel vibrations, you feel like a stimulation. They're like little pads that shock you a little bit. Yeah, that's using infrared waves actually to do that too. So the actual wave itself is causing your muscles to like stimulate and vibrate at a certain frequency. That it pretty much simulates somebody like massaging you. That's what it's supposed to be doing really. It's supposed to be helping the muscles to like loosen the muscles up. I mean, I know an application of it that's not on here. Can someone think of another one that's used for the military? Where would infrared be used military?
Oh, like to see people.
Infrared goggles.
Yeah.
Okay, or binoculars that are infrared. You'll see a lot of it. I mean, they did a whole, I'm terrible at history and social studies, so don't judge me. Who did we capture a few years ago? What terrorist was it that was a big deal? It was Osama bin Laden,
We
right?
didn't capture him, we killed him.
Was he
He
killed?
wasn't captured, he was killed.
He was killed, but they raided his house, right? And they were like, okay, it was like a stealthy operation with a new helicopter, right?
Still until their helicopter crashed.
Yeah, okay. So if they released like some footage of the actual, I guess the infrared cameras they were using, whatever the binoculars were, and it's pretty amazing to actually see what you can see with these things, because you're like almost seeing through walls. It's using like heat vision in a sense, if the signal, if the source of heat is enough. But you literally see the outline of somebody's body based on the actual camera. There's a new phone that just came out, maybe like 2 weeks ago, I saw it online, that has an infrared camera in it now. And you could literally see, you know why it's useful? Who could think of an application of it? Come on, quick.
Firefighters.
At home, why would you use it? Okay, firefighters, where are the sources of the fire? Very good, that's actually really, I didn't think about that. Where's the fire starting, right? It's a great point.
You could,
Okay, possibly at night. If you want to see if there's people in your yard at night.
and like your bedroom and stuff, and like, I don't know.
If the signal's enough, if they're not, like maybe they might have to do it against the wall.
general shenanigans.
General shenanigans, hunting, hide and seek as a game, okay? How about for like home improvement?
If you're a monster, all you build.
Ice crawlers.
What about pipes?
That room's not
Pipes,
crawling,
I mean,
then you can
like,
see.
so, the only thing that you could, like, so let's
Lots
say,
of
like,
night crawlers.
No, because then you can see. The room's night crawlers.
for example, if you're like trying to put up a TV or something, or you're trying to figure out something with your pipes, the only way you can really see where they were is either like knocking in like an irregular way, which you probably
Possibly by the hot water,
Or like-
pipe heat up and you can see it.
right, or like you'd have to like open up your walls, so this makes it a lot easier.
Yeah, think about what happens with pipes a lot of the time too, is pipes burst or freeze, there's two problems with that. So if a pipe freezes, you can find a location where it freezes, and then take a hairdryer to your pipe, sometimes in winter you have to do this on freeze your pipes. Or if it bursts or something, you can see that there's no water flowing through the next part, the temperature differential will be there for sure. Anything where there's a temperature change, even a stud in the wall where you have to nail into, you have to find the stud, I think it probably does use some sort of infrared waves. All right, visible light is our spectrum that we're going to use. So using optical microscopy, so looking in microscopes uses obviously visible light. Astronomy uses visible light. Photography itself. UV light. If you need to sterilize equipment, so you ever go to the dentist, you wonder what they do with those like picks after they're like picking at your teeth for a while and cleaning your teeth and like gross? Well, they get sterilized. Okay, with UV rays, they get sterilized. If you're looking for fluorescence, if you decide to take forensic science next year, you'll learn about searching for drugs. UV light is used for drugs. It's also used for general things for forensics, but specifically you'll use it for certain types of drugs to see if they're real drugs or not. It's one of the tests you use to verify that it's actually a drug and not some synthetic.
With a UV light, can you see a lot more stuff when like they're doing like, I don't know, when they're looking for fingerprints and stuff?
Yeah. It's exaggerated in TV a lot, but you do use it for crime scene analysis, absolutely. But it's exaggerated on TV is what you can actually see. X-rays. We know X-rays really were around. Why? For bones. That was the big deal for X-rays. Everybody knows you get an X-ray if you break a bone. Now, your teeth also use X-rays. Okay, your teeth as well. I don't know what vital organs use X-rays for, but I'm not sure. They probably are, but I never knew that. That was something new to me. I never knew that an organ would come up on an X-ray. I thought it was only the bones.
You can see your, like,
What, do you know which one specifically or no?
I mean, like, I got, like, my back X-ray and I
And you can see like your lungs and your liver, you could just see. It's probably because it uses X-rays and senses, I'm guessing the density, I have a feeling, has to do with. I'm not sure for that. And then some treatments for cancer use X-rays as well. Now, this next one is really cool. Gamma rays, I mean, treatment of cancer, obviously, we talked about already, but for food irradiation. So if there's pesticides on food, or if there's something to do where the food has been altered, this is a way to, in a sense, cleanse the food. But the other part that I like, and that I think is most interesting, look at this part. If there's a crack in a column in Grand Central, and the column, like, you know these columns that support the building itself? The column might be like 6 feet in diameter. How are you going to see a crack on the inside of it? You'd have to test with some machine that could cause it to vibrate and sense the vibrations of the waves and stuff. Well, they use gamma rays instead. Why do they use gamma rays? Because it's not going to propagate that crack. If there's a crack in the middle, and you vibrate too much, that crack would spread, propagate. You would not want to do that, obviously, but you could use the vibration to tell if there's a crack. You use gamma rays instead. Okay, and I have a feeling that based on how long it takes the gamma rays to pass through, you can sense that space or that crack itself. Okay, so these are our applications of the EM spectrum. Let's see some of the math we're going to use. First piece of math we're going to use is this constant here. This is a universal constant. It is the speed of all EM waves that travel in a vacuum. It's also known as the speed of light. Okay, the speed of light. You can't pass the speed of light, that's the whole concept. There have been a lot of theories about things like wormholes and these, not the correct word, but like a gateway to another location in the galaxy. If the galaxy is warped in a certain way, that you enter on one end, you come out on the other, and you cut through time. But it's never been proven yet, the whole concept. And that's part of Einstein's theory of relativity. If you've been studying and following up on science, you'll really know what happened recently.
Didn't something with his theory on relativity just happened?
Yeah, what was it?
Gravitational,
Waves.
yeah.
Gravitational waves were detected. It's like a huge deal. So gravitational waves has always been suspected, and they can kind of have an idea from tests. But remember how we talked about how like everybody has their own gravitational field, but like you can't really see a human's gravitational field. You can't detect it because it's not distorting the space-time around it enough. But it was detected, and I can show you a quick video and explains how it's done. Brian Greene, a great author, explains it really well. I can tell you how it works, but his explanation is a video of it's really cool. Brian.
That's why he was off.
You said the name of the phone.
Sorry, no,
He was too good for this. So
You really love quizzes.
yes, that's a good class. That's a great application. You read about it? So the idea of gravitational waves, here's the thing. We've never been able to study black holes because of the fact that when light enters a black hole, it's gone. A black hole is so dense that it pulls light into it. So the idea of gravitational waves being used to study black holes is going to be a big application. It's also going to help us with the idea of discovering really the concept of the Big Bang and learning more about the beginning of time. So if we have time, I hope we have time, I'll show you that quick video. So the speed of light is finite, okay? That is a maximum speed at which it can be attained. We're going to use that idea to talk about something later when we talk about light, how light could be bent by different lenses. So the first example is a very simple example. The FM radio band extends from certain ranges of frequencies. What are the longest and shortest wavelengths? So the first thing you have to recognize is that the velocity of all EM waves is the speed of light. And this is going to be on your formula sheet. You don't have to memorize it. Okay, but if I don't give it to you in the problem, you should know. If you hear that it's a gamma ray, if you hear that it's infrared rays, if you hear that it's ultraviolet, all of these travel at that speed right there. Anything on the EM spectrum that we just looked at travels at this speed. So that's our velocity. Our minimum frequency is what? I'm going to write a min and a max because there's two of them. We have a range of frequencies. I'm going to list both. The minimum frequency is 87.5. Now mega, remember, means times 10 to the 6 hertz. It's megahertz. Okay, megahertz. Both units are megahertz. 87.5 and 108. The largest frequency is 108 megahertz. That's our minimum and maximum frequency for the FM radio band. When you tune in on the FM, you never go beyond 108. You don't look back at the beginning. Where does it start? It always starts around 88, 87.5. Okay, that's the FM radio band. So, you could make your own radio station. All you need is something to send out the signal. People out in the country, out like, places where there's not cities, there are a lot of empty radio bands. So if you want to make your own station, tune into tell people 89.1, that's my station. As long as you're in like a 2-mile radius and you have the strongest signal, the strongest amplifier that can give that signal, you will be that station. You can sit there and make your own radio station. A lot of people do that. They broadcast live. A lot of people now obviously use, instead of that, they use live streams online instead of this method. But this method is still used. Okay? So those are the two frequencies of the range. We need to find the wavelengths. So what is our formula here that relates these? We want to find our wavelengths. What's the formula we're going to use to find them? Yeah, what do you got?
E equals wavelength times frequency.
Yeah. Okay, velocity equals wavelength, or frequency times wavelength I wrote, or wavelength times frequency, either one. So what we're going to see is, when we have a higher frequency, remember we have a lower wavelength. So we'll see that the maximum frequency will give us the minimum wavelength. And the minimum frequency will give us a higher wavelength. So let's just go ahead and solve for lambda. You've seen this already. We looked at this formula already once, but now we're applying it to EM waves. So there's the velocity in meters per second. The minimum frequency was 87.5. I'll do that one first. And then that's going to give us, obviously, if we use the minimum frequency, the maximum wavelength. So let's put max down here. Okay, that should be understood by now. We've done this enough. The last couple of days, or last week, we talked about frequency and wavelength a lot. So you can calculate what the wavelength becomes. I think we're going to have the cancellation there of those units. But then that'll be 300 over 87.5. It's going to give us, in this case, 3 point, what do you got? Yeah. Okay, around 3.43 meters. And to get the minimum wavelength, you're just going to change this number up right here. This number right here becomes 108. Do the exact same thing on your calculator. Hit second enter maybe to pull up the same command you just entered to do this. And just change this number to 108. Okay, and I know my units are in meters because I have meters per second, hertz, which is really 1 over seconds, which means the seconds cancel in both spots up there, leaving behind meters. For this, you're going to get 2.78 meters. And that's going to be the minimum wavelength. Okay, so the wavelength of the FM band does not extend very far in the wavelength. From 2.78 meters to about 3.43 meters. All right, the last slide I want to talk about is something that I find, but the reasoning is not always clear. So the brightness of light, the concept that as you get further away from the source, the brightness decreases. Now, you can read about why it is, you can visualize or think about it, but think about area. Think about area. The area that you're shining the light on when you're close is a small area. Then it's a larger area. Then it's an even larger area. But the amount of energy that's coming out of the bulb or the flashlight is fixed. It's a constant amount of energy. It's not increasing. So the same amount of energy concentrated is like a high density, if you will. As you move further back, the area increases. And it's increasing in a way that area would. So it's approximately equivalent to the actual distance over the new distance. The difference in those? Squared. The difference in their factors. So realistically, if you double the distance from the source, the brightness should go down by a factor of 4. If you triple the distance, it should go down by a factor of 9. Now, that's the theoretical idea. I tested it today. So we have there's a probe here, and I can show you the probe. I'm going to put the time lapse down. Show you what the probe looks like. And when I tested it, and I was going to show you guys, but when I tested it, what I noticed was that it wasn't exactly right. I doubled, so this measures in lumens, is the unit, I think, lumens for light luminosity or brightness. So I connected this to a vernier sensor, tested it in a certain range, and what I noticed was when I doubled the distance, it didn't go down by a factor of 4, it went down by a factor of 3.5. Then I tried it again, and I did it from like 5 centimeters to 10 centimeters. When I did it from 10 to 20, it went down by a factor of like 3.7. So what I was noticing was that it does almost go down by that factor, but I feel like the distance from the source initially needs to be far enough that it's not being overwhelmed with the light in the beginning. I'm not sure really how it works, to be completely honest. But when I doubled the distance at a further rate, it was almost close to being a factor of 4 in decrease. It was like 3.7. But the concept here of the actual line decreasing, think about the fact that you're spreading light over a larger area, and area is measured in square meters. Okay, so think about the fact to remember that this is approximately the square of the factor of increase for the distance. So if I increase my distance from like, I don't know, 2 to 6, right? 2 to 6, it's a factor of 3. So the the brightness of the light should go down by a factor of 9. Just square whatever the distance increase is by that factor. All right, let me show you that video real quick, or see if I can pull it up.